Imagine a child learning to ride a bike. They wobble, they fall, they get back up. Each attempt, a lesson. Each success, a reward. This, in essence, is the heart of reinforcement learning, a powerful type of machine learning where an agent learns by interacting with its environment. Through trial and error, guided by feedback in the form of rewards, the agent learns to navigate complex situations and make optimal decisions. Unlike traditional supervised learning, where models learn from labeled data, reinforcement learning thrives on exploration and discovery. It's about learning from experience, much like humans do. This makes it particularly well suited for scenarios where explicit instructions are unavailable, and the best course of action needs to be discovered through interaction. This approach opens up exciting possibilities for artificial intelligence, AI. We can now build systems that not only analyze existing data but also learn and adapt to new situations in real time. This dynamic learning process is what sets reinforcement learning apart, enabling machines to solve complex problems that were previously considered the exclusive domain of human intelligence. Reinforcement learning is not just an academic curiosity, it represents a fundamental shift in how we design and build intelligent systems. Its ability to learn from raw experience, without the need for vast amounts of labeled data, makes it incredibly powerful. This is particularly relevant in fields like robotics, where collecting real-world data can be expensive and time-consuming. Moreover, reinforcement learning allows us to tackle problems that involve sequential decision-making in uncertain environments. Think of a self-driving car navigating a busy city street. It needs to constantly process information from its sensors, anticipate the actions of other vehicles and pedestrians, and make split-second decisions to ensure safety and efficiency. This level of complexity and uncertainty is where reinforcement learning truly shines. From personalized recommendations in e-commerce to optimizing energy consumption in smart grids, the potential applications of reinforcement learning are vast and rapidly expanding. As we continue to push the boundaries of AI, this approach promises to unlock new possibilities across industries, transforming the way we live, work, and interact with the world around us. At the heart of every reinforcement learning system lies the interaction between two key components, the agent and the environment. Think of the agent as our learner, the entity that we are trying to imbue with intelligence. This could be anything from a virtual robot navigating a maze in a computer simulation, to a physical robot learning to grasp objects in the real world. The environment, on the other hand, encompasses everything outside the agent. It represents the world in which the agent operates, complete with its own set of rules, dynamics, and challenges. The environment presents the agent with situations or states, and it's up to the agent to learn how to act within these states to achieve its goals. This interaction between agent and environment unfolds as a dynamic interplay. The agent takes an action which in turn affects the state of the environment. This change in the environment is then fed back to the agent, along with a reward signal that evaluates the effectiveness of the agent's action. This cycle of action, feedback, and learning repeats, allowing the agent to progressively refine its behavior and become more adept at interacting with its environment. In the world of reinforcement learning, rewards are the driving force behind an agent's learning process. They act as the feedback mechanism, telling the agent whether its actions are leading it towards or away from its desired outcome. A positive reward signals a good move, encouraging the agent to repeat similar actions in the future. Conversely, a negative reward, often referred to as a penalty, indicates an undesirable outcome, prompting the agent to adjust its strategy. The concept of rewards is directly inspired by how humans and animals learn. Think about a dog being trained to fetch. The joy of receiving a treat and praise reinforces the dog's behavior, making it more likely to repeat the action of fetching in the future. Similarly, in reinforcement learning, carefully designed reward systems guide our artificial agents towards achieving their goals. It's important to note that rewards don't specify a task should be completed, only the desired outcome is. This distinction is crucial, as it allows the agent the flexibility to discover novel and creative solutions that we, as designers, might not have anticipated. This open-ended learning paradigm is one of the most powerful aspects of reinforcement learning, enabling agents to go beyond simply mimicking pre-programmed instructions and instead learn to solve problems in innovative ways. Section 3. Actions and Policies. Navigating the decision space. At every step of its interaction with the environment, an agent is faced with a choice. What action should it take? These actions form the agent's repertoire, the set of possible moves it can make to influence the state of the environment. The nature and complexity of these actions can vary greatly depending on the task at hand. For a chess-playing AI, an action might involve choosing a piece to move and its destination. For a robot navigating a room, actions could involve rotating its wheels, adjusting its arm position, or interacting with objects. The agent needs a strategy, a game plan to help it decide which action to take in a given situation. This is where the concept of a policy comes into play. In reinforcement learning, a policy dictates how an agent selects actions based on its current perception of the environment. It can be thought of as a mapping between the state of the environment and the actions available to the agent. A simple policy might be deterministic, meaning that for a given state, the agent will always choose the same action. However, more sophisticated policies can be stochastic, introducing an element of randomness into the agent's decision-making process. This allows agents to explore different possibilities and avoid getting stuck in local optima, ultimately leading to more robust and adaptable learning. Section 1. Unveiling the learning algorithms, Q learning. Now that we understand the basic ingredients of a reinforcement learning system, let's explore how agents actually learn to make good decisions. One of the most popular and influential algorithms in reinforcement learning is called Q learning. At its core, Q learning is all about learning a value function, represented by the letter Q. Imagine this Q function as a lookup table, where each entry corresponds to a specific state-action pair. The value stored in each entry represents the agent's estimate of how good it is to take a particular action in a particular state, considering all future rewards it might receive as a result. The higher the Q value, the more desirable the action in that state. Initially, this Q table is filled with arbitrary values, reflecting the agent's lack of knowledge about the environment. As the agent interacts with the environment, experiencing rewards and transitioning between states, it gradually updates its Q values, moving closer to the true values that reflect the long-term consequences of its actions. This iterative process of refining the Q function lies at the heart of Q learning. Section 2. Beyond Q learning, policy gradient methods. While Q learning provides a powerful framework for learning in discrete action spaces, what happens when the number of possible actions becomes incredibly large or even continuous? Think about controlling a robot arm with multiple joints, where each joint can move smoothly through a range of angles. In such cases, using a Q table to represent all state action pairs becomes infeasible. This is where policy gradient methods step in, offering a more elegant and scalable approach to reinforcement learning. Instead of learning a value function and then deriving a policy from it, policy gradient methods directly optimize the policy itself. They treat the policy, which maps states to actions, as a parameterized function and use gradient ascent algorithms to find the parameters that maximize the expected cumulative reward. Imagine navigating a hilly terrain where the elevation represents the reward signal. Policy gradient methods are like a hiker who continuously adjusts their direction of ascent based on the local slope of the terrain, ultimately reaching the peak, which corresponds to the optimal policy. This direct optimization of the policy makes policy gradient methods particularly well suited for complex tasks with high-dimensional or continuous action spaces.